Yeah, so today is the Geophysics day of the summer school. There will be a bit of more geophysics next week as well, but today will really be quite a lot. So what I'll try to do to start off here is to say a little bit about what environmental geophysics is. Obviously, there are other terms that other people are using, hydrogeophysics, near-surface geophysics, and so on, and they're a bit synonymous. But environmental geophysics for me is basically the use of geophysics for environmental applications. Then I will briefly introduce the underlying principles of the most common geophysical techniques. Not sure if I'm going to get to gravity and magnetics, but then at least the basic geoelectrical, electromagnetic, and seismic methods will be treated. I will not talk really about case studies. I think this will be given by the lectures later on in the afternoon. And I will also not talk about monitoring applications. I'm sure that, for example, Kamini will have a lot of applications like that. So I'll try to just stay on the basics here. Okay. Environmental geophysics, that's not new. So sometimes people that come outside of geophysics, they say there's this new thing called geophysics. I mean, there is this 3-volume textbook about geotechnical and environmental geophysics from 1990. Very detailed. Not totally up to date, of course, but it's still quite there. There's a good textbook from '97, Sharma, still one of the better ones, I think, for a general course in environmental geophysics. And then, of course, geophysics has been used for water prospection for decades. This is a summary of some 20 years of work in Southern Africa, so something that is not new. What is also not new is the basics of many of the geophysical techniques that we use. So I think this is just something that is important to remember. The self-potential method, for example, I'm going to mention, sort of first used almost 200 years ago. Electromagnetic induction developed some 100 years ago in Scandinavia and Russia. Magnetic method also by Swedes. I'm saying this since I'm from Sweden. The ERT, or the electrical measurements, by Schlumberger. I think also Andrew Billy will say that there's someone from the UK, also a little bit before, but basically it's a bit more than 100 years ago, okay? Of course things have developed, hardware, software, understanding, applications, but we need to remember that we're building on something that is pretty mature. What we want to do is that we want to provide information about properties, processes, and states at scales that are relevant for a given application. So in this figure here, we could start, for example, at a basin scale or watershed scale, and we may be interested in the stratigraphy. So we will use different types of techniques to say something about different geological units, and we use this to build a hydrological model. Could be an application. We might go to a hill slope scale, look on river groundwater interaction, movement of a contaminant down here, or we might be interested in something happening at the pore scale. For example, microbial activity that releases some gases. We don't see the microbes, but we might see an accumulated response of many microbes that work together. So basically, we can have information about processes and properties at very many different scales. And that's, of course, one of the strengths when we use geophysics. When we go to larger scale, at least for a given budget, basically what it means is that the details that we can resolve, so the resolution of our images, will be lower, or the resolution is larger, so we say that that's a worse resolution. So airborne method, satellite measurements for countrywide, county-wide applications, surface-based measurements, if you're maybe at scales to some kilometers, cross-hole at scales of tens of meters, and then logging at scales often less than a meter in spatial resolution. And then, of course, you can do laboratory work and very advanced imaging at the millimeter scale or micron scale. So the promise here, to summarize this introduction, is that we want to use geophysics to obtain spatially extensive information. So that means essentially 3D. So we want to be able to have an image of a physical property that is varying with X, Y, and Z, and hopefully also with time, if time plays a role. So in 3 spatial domains, 1 temporal domain. We want to do it in a way that is minimally invasive, so we don't want to affect the system or nature when we do this. It has, of course, to be cost effective. And that resolution here has to be high enough to be meaningful for an application, and we want to accommodate this with some uncertainty quantification of what we're doing. Without any UQ, basically it's very difficult to do something meaningful. The challenge here is basically twofold. Geophysical models are resolution limited images of physical properties, so we're not providing a perfect image. It's not a photograph of the subsurface that we're going to get. It's a blurry image of the subsurface, and we need to account for this. And that has been one of the developments, I think, in, let's say, in hydrogeophysics in the last, I guess since 2000, this recognition that the fact that your images are not perfect images of the subsurface has quite some consequences if you want to use them for hydrogeological applications. And then the other one, of course, is a bit the hidden thing here, or the elephant in the room, is that the properties here, electrical properties or others, they are indirectly related to what people are interested in: slope stability, soil structure, permeability, water content, or something else. So we need to remember here that geophysics will only be useful if physical properties can be linked in some way to what you're interested in. Okay? So if you want to be successful, this is a little bit my recipe here, very briefly. You need to have a well-defined objective, so you need to know why you're going to use geophysics. And then you need to talk with people that know something about geophysics if you're not the expert. So you need to define a survey that allows you to actually have a chance to respond to that objective. There are many cases where people maybe want to see, I want to see a fracture at 200 meters depth. The aperture is 1 millimeter, and I'm going to do whatever, ERT to do this. It's not going to work. So consider things beforehand, do proper analysis, and you will actually be able to use it for what it's good at. You need to acquire high quality data, not only meaning the right method, the right instrument, but also knowing what you've been measuring, so being meticulous in the field. Again, it's something that is boring, perhaps, but if you don't really know what you did in the field, garbage in, garbage out, right? So you're sort of lost. You need to be careful here about these relationships. They can be qualitative, they can be quantitative, but you need to have a reasonable and honest assessment of how your physical properties will relate to what you're interested in. Because your images will be high resolution and nice, comparatively speaking, but if they are not really related in an obvious way to what you're interested in, it's essentially useless. So that's something that is really important, and I think that's something that has developed quite a lot in the last decades, this sort of recognition that one has to work much more on thinking about how to adapt the link between physical properties to near-surface properties or environmental properties. Before, this was done a little bit too simplistic, I would say. And then, of course, you need to do inversion. I'm going to talk about the probabilistic approach later on today. Fred Guyon will talk about the deterministic approach. So basically, you need to do a targeted parameter estimation to get something that is robust in terms of the properties, ideally directly targeting the properties of interest and not the physical properties. So when we start here with a technique, this is the electrical method. I start with this one because it's quite easy. It's basically based on Ohm's law. So you have an electrical field. And this is just an empirical relation. So you have electrical field is linked by a resistivity and a current density. So how many amperes passes a meter squared of surface. You inject a current. So you can if you inject a current, let's say 1 ampere, we normally inject a bit less, of course. You can calculate this current density, because if you start now assuming that your resistivity is uniform, it's going to move as a half sphere. No current is going to go in the atmosphere. So we know that the circumference, or the area of this half sphere, is 2p r squared. So we have now a link. We're not working with the electrical field. We are working with electrical potential. We define this as the derivative of so the derivative of the electrical potential is minus the electrical field. So we have a relationship here. We integrate, and we have that the electrical potential is resistivity, current, divided by something related to geometry. Then in practice, you can just not inject a current at a given location. If you have a source, you need to extract that current at some place, so you have a sink. And luckily, with the electrical method, you can apply superposition. So you can calculate, for example, if I inject current here, I can calculate what is the potential in C, what is the potential in D due to A, what is the potential in C and the potential in D from B, and then I can just take the difference. So I don't have to consider them together. So that's something that makes modeling quite efficient. So then I have an expression here for the potential of C, potential of D, based on injection in A and B and the distances in between. We cannot measure potentials. We're measuring voltages. These are differences in potentials. So we take the difference between UC and UD, and we obtain a relationship here. And we can rewrite this a little bit as the resistivity being a voltage, what we measure with our instrument, a current, which we inject and also measure, and a geometrical factor that just relates to where we are measuring with respect to, so it's the geometrical information. Okay? So this is what happens, and it's the solution, let's say. You get directly your right electrical resistivity from one measurement. Of course, resistivity is not constant in space, so this measurement, we call it an apparent resistivity. It gives an average of the subsurface at a given scale that is related to the separations of the electrodes. And when you now increase the separation between the electrodes, you're going to average over larger and larger scales. So if you, for example, take this first case here, you have a first layer that has a low resistivity, higher resistivity here in the middle, and then half space, so a low resistivity that just continues to infinity. You're going to, by increasing your separation, you're going to get this sounding curve. So you're going to see something not so resistive, more resistive, less resistive in a sort of smoothly varying behavior, because again, our measurements is an average, and we're going to average just over different scales. And to get this from here to a model, that's why we do inversion, and I'm not going to talk about it in this lecture. ERT, electrical resistivity tomography or resistance tomography, is the basic thing. For electrodes, you increase the spacings and you move along. So you get measurements at different separations, at different horizontal locations, maybe in two horizontal directions. You increase the spacing and you see more in depth. And from inversion, you can obtain a model. We'll call it often a tomogram. Here's just a simple example. We measured across a river in Switzerland, and we are made an interpretation here. So we say loamy topsoil, we say gravel aquifer with some heterogeneity, lacustrine clay. So how did we get there? Well, what you need to know is you need to say something about geology. So you have some information about the geology that you observe or that you know about, and then you have these petrophysical relationships. Here's just one model. There are literally hundreds of electrical petrophysical models, but I just show this one because it's just in a linear form, and it's a bit easy to interpret, and you see all the factors that affects the electrical conductivity of a soil or a rock, a porous rock, where you have water or you do not have water. So you are in sort of water-air systems here. So what is affecting your electrical conductivity? Well, many things that are of interest in environmental application. Porosity, M, is an indication, it's something that increases when connectivity of the pore space decreases. So you have information about connectivity of the pore space. So some possible link to permeability. Water saturation, N, essentially measure N is increasing when the connectivity of your water phase is decreasing. So you also have some information here that is relevant. Conductivity of the water, basically a proxy of salinity. And then surface conductivity, that is essentially related to the specific surface area. So if you have a lot of surface area, you get a larger surface conductivity, so for example for clays. So the problem here is, I mean, the nice thing, you're sensitive to many things of interest, but you're sensitive to all of it at once. So how do you solve this? Well, first of all, you use, for example, ERT, and you get these maps to say something about 3D heterogeneity, or you do monitoring to see changes in time. You need to know what you do in terms of data errors, measurement configuration. You need to have a contact between the electrodes that you inject in the ground and the ground. You need to have information about topography, and you need to have reliable codes that accounts, for example, for the dimensionality of your problem. So if most of these applications here. This is what we call a 2D inversion, but it's not 2D in the sense that we assume a sandbox in 2D where we just have a limited y direction. What we just say by 2D, or we often call it 2.5D, is that all the heterogeneity occurs with depth and along the profile direction. So basically our model is assuming that this little thing here is just continuing to plus infinity and minus infinity. This is an assumption that we're making, and of course if you have 3D profiles you can do something that is better than that. Induced polarization is adding some information to this, because in addition to looking on the conductive properties of the subsurface, you're also trying to say something about the capacitive properties. So basically the ability of a soil to store charge. They can be related to polarization at the mineral-water interface or in pores. I think that's Andrew Huseman and probably Andrew Binley. They will both talk more about this later on. But it has a very nice feature here, because with the electrical conductivity, you cannot distinguish between something that is saline or something that is clayey. When you use IP, you're going to get a strong IP response if you have a high specific surface area. So in this way, you will be able to say something about a high conductivity being due to salinity or clay, and that's of course important in a contaminated site investigation. So here is the idea. This is the time domain setup. You inject your current, a square current. This is the same thing you do with ERT. And then what you observe is that the voltage that you measure, it do not go directly to zero. It decreases with a certain delay. And this delay here, we're going to use to say something about these capacitive properties. The classical approach would be to estimate the chargeability, which is basically the ratio between this secondary voltage over the primary voltage. And we will see that this chargeability is going to be sensitive, strongly sensitive to clay content. When you do these measurements, IP, and also another method I'm going to talk about later, self-potential, you need to use what's called non-polarizing electrodes, because if you would use normal electrodes, you would get this type of decays changing over time that will just be related to the electrode potential of the electrodes that you're using if you use, let's say, stainless steel. So you don't want to do that. So you want to use non-polarizable electrodes. Doesn't mean that they do not have an electrode polarization. There's a potential difference of 100 millivolts or so between the electrode and the ground. It's only non-polarizable means that the potential of the electrode do not change significantly, or ideally not at all, as a function of the current that runs through this system. So basically your electrode reaction is fast and you are in a stable environment. So typically you have the actual electrode here, and then you have some sort of saline clay mixture here that ensure that the salinity in this region is constant over time. There's a whole theory here describing why you get this polarization with IP method, and I think this will be touched upon later on today. But basically, traditionally at least, you talk about membrane polarization. So this is related basically to the fact that the surfaces of minerals are typically negatively charged. So you have an excess of charge around those, and that will prohibit certain ions to move. So you will get a charge up, a build up, a concentration of positive or negative ions in, for example, pore constrictions, or on a grain. When you have a current going, you might have a polarization of the grain. So the positive charge will move to one side of the grain, and then it will diffuse back when you stop the current. And this is partly responsible to the IP effect. Then you have electrode polarization. If you have metallic objects, so your current is flowing, you have to build up a potential jump when you go from electrolytic to electronic conduction. And when you stop the current, this sort of battery will sort of discharge and you will get a response. You can also measure spectral IP. So instead of measuring in the time domain, you measure in the frequency domain. You have an alternating current. And due to this capacitive effect, you will have a phase lag on your voltage that you're going to measure. And this phase lag now is indicative of the of the capacitive properties. Okay? Problem is that it's difficult to measure and it can be quite time consuming in the field, at least if you want to go to low frequencies. So just a last slide here on IP. So for example, Lee Slater and Lesmes here in 2002, they suggested, I'm not sure if they were the first, but they suggested some normalization of the IP parameters. So you look on either what we call the imaginary conductivity or the chargeability divided by the resistivity. If we do this, the IP parameters become very indicative of specific surface area, whereas the chargeability in itself is related also to other contributions, like for example the salinity. So in this way, you can essentially, by combining the conduction and capacitive properties, you can essentially distinguish yourself here if you're located, for example, if you have a large imaginary conductivity and low conductivity, well, you're likely to be in a clay sand, maybe in partial saturation. If conductivity is high and your imaginary conductivity is high, well, then you're in a clay sand, but it's also a saline system. So by doing this, you can disentangle and it sort of show the value of two pieces of information, and you can say something more about the system being studied. So yes? So the imaginary conductivity would just be, if you would now imagine that one cycle like this is 360 degrees. And now you would say that, okay, let's say this is t, and if say this is delta t, the delay. So if you take delta t over t and you multiply by 360, you would essentially have your phase. So this is what is indicated here. You have the real part, you have the phase of the delay, and if you now look, instead of describing this as a magnitude and a phase, you can describe this as a real part and an imaginary part. So it's essentially a measure of this delay that is occurring. Okay. So so the idea here is that you get some more idea about electrochemical properties of the subsurface. So you get information about mineralization, grain size, clay content, some cases even permeability. You can resolve this ambiguity between clay and salinity. Much more difficult to acquire high quality data than for DC resistivity. And there are still some unknowns explaining really how this is working, especially perhaps in under unsaturated conditions. The self-potential method now is also using non-polarizing electrodes, but what you do is that you do nothing. You basically have a voltmeter, you have those non-polarizing electrodes, and you're measuring the naturally occurring potential field or voltages with respect to a reference electrode and other electrodes. So you look here on current systems that have been created by Earth, not by mankind, at least not primarily by mankind, and we want to use this naturally occurring potentials that are indicative of currents floating around in the subsurface to say something about something that we might be interested in. So it's a passive method. So in geophysics, methods essentially where we have no active sources, self-potential, magnetics, gravity, they are all passive. They are often potential field methods. And then many other techniques are active. DC resistivity I talked about, induced polarization, we inject a current. Electromagnetics is also considered to be an active method, even if you sometimes don't inject your own source, seismics, and so on. Now, of course, there's a bit of a link. There's, for example, passive seismics that is developed a lot. So then you can maybe argue that part of seismics is also a passive method. Anyway, with self-potential, you have essentially three contributions that are important. One is related to water flow in a charged porous media. You have electrical double layer, so you have a lot of cations typically in this double layer. They are going to be dragged with the water flow. This is creating a charge imbalance, and you're going to get a current, and this current has a potential associated with it, and you can use it to say something about groundwater flow or vadose flow patterns. You have diffusion processes, so if you have a contrast in salinity, a contaminated region, a plume, and a non-contaminated site, you're going to have your cations and anions, and they are not having the same mobility. So since they don't move with the same space, the one with the higher mobility is going to move faster, so it's going to spread faster than the other one. This is creating a charge imbalance, and you're going to have a current that is going to be put in place to essentially ensure that microscopically your electrical charge is 0. And then there's the redox potential here. Sometimes you will have responses related to redox processes. So streaming currents, basically electrical double layer. So you have an excess, typically of positive charge. Fluid flow will pass. This will create a charge imbalance. You get a current in place, and then you get a potential that you can measure. So here is the old example, some almost 50 years ago. You pump in a well somewhere in Russia. You have a drawdown, and you get a self-potential signal here measured on the surface that is very reminiscent of the drawdown that has been observed with a number of observational wells. So this is one application of the streaming potential contribution. The electrochemical coupling part, as we said, is due to ionic fluxes because they have different mobilities, the different ions. And then we have the redox one that is related to electronic conduction in conductors. So electrodiffusive potential here, basically if you take sodium chloride, the sodium is going to be hydrated, so you have some water around it, so its mobility is going to be lower. So if you now have sodium chloride at the location, the chloride will diffuse much quicker. So if this is the original plume, the chloride at some point will be here, whereas the sodium will just be here. And this creates basically then a charge imbalance, and you get a current in place and a potential that we can measure. Then we have the redox potential contributions here. So when we have reduction, we essentially take up an electron, and when we have oxidation, we're going to produce an electron. And the electrons will not like to be there by themselves, so you have essentially reduction and oxidation always occurring at basically the same time. So this is a coupled process, and they will occur at different locations ideally. So if you have a metallic object, let's say a metallic drum in the subsurface with some toxic material, you will have reduction on the surface, oxidation at the bottom, and this will typically create a very strong negative self-potential signal that you can use to, for example, locate this metallic object. In short, summary here, self-potential. So some of the response is related to water flow. So you're sensitive here to the spatial distribution of flow. Electrical conductivity plays a role. So often you would do ERT to get an image of electrical conductivity, and you will need to use this to tell for a given current system, you need to know the electrical conductivity in order to calculate what the potentials should be. And then you need to know something about this coupling, which is essentially a factor related to permeability, specific surface area, clay type, and so on. Yes?
Can you get the flow velocity with that?
There are a number of applications where you can do that, yes. So there are applications where, for example, you say something about the Darcy velocity, for example. So that's something that you could, in theory, do. The problem here, what's that?
Or so they say.
No, I wouldn't say that. So what I wanted to say is that it's not so easy. So it's not so easy, and because you're superposing, there's a superimposition of multiple contributions. So this was the first contribution. So the problem is that in many SP studies, people will say, this is the only contribution, okay? But then we said, okay, so if you have some variations in salinity, you have this electrodiffusive contribution. If you have some metal, you have another contribution. And then you have noise, so you have telluric currents related that you use for deep EM sounding that will add some noise. And you also have the electrodes that are not necessarily as stable as they would like to be. So you have electrode effects that is adding to this. So from a theoretical point of view, it's pretty straightforward. In practice, it's not easy. But it's used. I mean, it's used traditionally, for example, on volcanoes to get idea about large-scale flow patterns, and it's been used since 40 years for this to get an idea about the main flow patterns, saying something about the expected depth to the water table and so on. So, I mean, it has been proven to be useful for, it's really one of the common techniques of geophysics on volcanoes. Since you cannot carry so much things, it's working not bad. All right, electromagnetic methods now. You're still targeting electrical conductivity, so like ERT. The big advantage here compared to ERT is that you can work on basically any scale, so sub-meter scale to mantle scale. You do not need to have a coupling to the ground, so you can measure with the satellites, helicopters, ships, tractors, and so on. And you can, of course, measure in the ground as normal as well. Problem really is if you're in an anthropogenic system, so close to agricultural site, industrial site, you often have a lot of EM noise that makes it difficult. And basically, there are hundreds of EM methods, but they have sort of two families. One is frequency domain EM, and one is time domain EM. So electromagnetic induction, this is Maxwell's equations here at work. So here is a case where you have a source, an alternating source, alternating current with a known frequency. It will move in this coil. This coil is placed on the surface of the Earth. When you have a current, not just an alternating current, but just when you have a current in the Earth or in the coil, you will have an associated magnetic field. You always have that. When the magnetic field or the magnetic induction is changing over time, as it will do since you have an alternating current, the magnetic field and the magnetic induction will change over time. When this magnetic field impinges on a conductor, so something that is conductive, you're going to have induction occurring, and induction will basically say, I'm going to put into place an electrical voltage that will drive a current here, we call it an eddy current, that will oppose the change that the surface of this conductor is experiencing at a given time. So basically we'll try to, it is a conservative force, if you like, so you try to oppose the change in the magnetic field. And now you have a current in place. This current that is in place creates a magnetic field. This magnetic field will change over time. It will decrease over time. And since it will change over time, you will induce a current here in the receiver coil, and you pick it up as a voltage, and this is what you're going to use. So basically, this is the overall principle of EM induction. Here are essentially the two laws. You have Ampere's law stating that for a given current in the ground, you have a perpendicularly oriented magnetic field. For a changing magnetic induction over time, you have a resulting electrical field. And then you have three constitutive relations. So you have Ohm's law, we already saw, current density equal conductivity times electrical field. And we have a link between H and B, which is essentially that B is the magnetic permeability times H. And then we ignore here essentially high frequency effects. So we're not going to talk about this here at the moment. So essentially displacement currents we are ignoring. So how can it work? Here is one of the most beautiful systems that are around. This is the SkyTEM system from Aarhus University that has been developed for environmental applications, so for the upper 150 meters or so. Basically, you have your source current here that is looped, so it goes for a number of turns. And then you have a receiver coil at some location. You create this time-varying magnetic field. It induces eddy current in the subsurface, and a magnetic field will come back, and the changes in this magnetic field will be picked up by the system, and we will use this to say something about the conductivity of the subsurface. And here's a case study I liked. I think I showed it the last two summer schools as well. So they've been flying here in Galapagos Islands, Santa Cruz Island, 4 days. They're covering a big part of an island that is not poorly known in terms of hydrogeology.
Sorry?
Yes? It's all taken account for. So this is, of course, the complicated things here. So they will really monitor this in great details, and they will correct for this. So anything you will do. So basically, beforehand, people often used airplanes, and then it would be more stiff, and you wouldn't have these problems. And essentially, new technology has allowed you to work with helicopters, so you can go slower and lower, and you get higher resolution. But this is all accounted for in the processing. So this is really in the system. Otherwise, of course, you would have problems. Yeah.
Sorry, you say higher resolution. What do you mean?
So basically, if you can go if you can use your source here at a lower elevation, you will have the information that you will pick up will be an average over a smaller scale. So since you now can measure, you can maybe go here at 80 kilometers per hour, you maybe can have a measurement every 10 meters. So on the profile, you can get quite some information about what you're interested in. So here you can obtain some cross-sections, and you can then use them to make a hydrological interpretation. Here is the saline water coming in under the island. Here is a potential aquifer, and so on. So with some of these petrophysical laws, you can say something, and you can make a first interpretation. Then there's the frequency domain method, a bit more simple, but many of you have used it. We call it conductivity meters. You measure the secondary field, so this is what is caused by the eddy currents. You divide it by the primary field, and under specific circumstances, you can directly relate this ratio to an average conductivity. So for agricultural applications, you can essentially very quickly create a map that shows at different average scales what is the average conductivity, and you can say something about well-developed, poorly developed soils, contaminated site, less saturated sites, and so on. So EM methods, that's where I did my PhD some time ago. They have a very wide application in terms of space and targets. Primary advantage with respect to resistivity, it's quicker, larger depth of investigation is possible, no ground contact is needed, and you're highly sensitive to conductors. The negative sides, you're not very sensitive to resistors because you don't create any eddy currents. Physics is more complicated, so modeling is more complicated. You're very sensitive to EM noise, so it's very difficult to work in certain areas. Seismics now. In seismics, you will typically have some source, a hammer here. You will have some geophones that will measure the vertical movement of the soil or the acceleration of the soil. And you will do this in different combinations to try to say something about the basically the mechanical properties of the subsurface. So we work here at frequencies from 10 hertz, so go deep, to about 10 kilohertz. This would be cross-hole measurements over a few meters in hard rock. So we send a seismic pulse in the earth. It will travel down. It will interact with the subsurface, and some of that energy will return. We will use this returning energy to try to image the subsurface. We will use many sources and receivers, and in oil industry, they are sort of targeting, they have this sort of dream about 1 million receiver type of things. But now it's still there, I think they're probably at 100,000 or so. So it's really massive deployments for oil industry. Of course, you cannot really afford it for environmental applications. So many different types of waves. The body waves are the ones that travel in the earth. They're not affected by the surface. There's the P wave, and it's the S wave. P wave, you can think a bit about you queuing to a nightclub. I push you in the back. The next person pushes, and everyone is getting pushed very quickly. Whereas the S wave is a little bit more like you have a rope, and you make a turn like this with a rope, and the movement is like this. It's very simply speaking. So S waves are slower, P waves are faster. Velocities will vary from some 100 meters of seconds in the near surface to up to 8 kilometers per second in the upper part of the mantle. Typically, rock would be sort of 2 kilometers per second up to 4, 5, 6 in environmental applications. Velocities mainly depend on mineralogy, texture, porosity, types of fluids, confining stress, pressure, and temperature. Quite complicated, and people working on the link between seismics and those properties, they call it rock physics, but it's a whole field in itself because, of course, in the oil industry, there are many billions waiting for the people that want to work on these things and do it successfully. So here is an example, just briefly. VP velocity, VS velocity as a function of porosity. So at first order, you're basically sensitive to porosity, but then, of course, it's much more complicated than that. What is happening? Well, you inject this energy, it travels down. If you now think about one little object here, that is different than the surroundings, you have essentially Huygens principle, so you will get a secondary source. So when the wave touches this diffractor, you will have a secondary source. It's a bit as if you would be on a lake, you throw in a stone, this stone creates a wave, there's a rock in the pond, and when the wave touches this rock, the rock will essentially create its own wave that is going to move out. And what we're going to measure now is basically what we're mainly interested in is that energy that is going to come back. So you need to have contrast in acoustic impedance. So that's Vp velocity times the density. If you sum many diffractors, so here's one diffractor, here's many, and when you sum them all up, you basically get what's called a reflector. So this is a more like an interface between two different types of soils or rocks, and you get this secondary wave that will reach the subsurface. Seismic modeling and acquisition is quite complicated. You cannot just use the time at which your energy is coming back to the surface. You need to do what's called migration. Migration will replace all your measured section, your time section, in space. So otherwise, your depth and geometry will not be really correct. Here is an example. Here is some time section of some various reflectors. It all looks like diffractors, so some localized objects here. When you do migration, you essentially see that there is this surface here, undulating surface, and if you don't do migration, well, you couldn't really see this type of interface here very well. So it's a whole science in itself, and seismic reflection is not really used so much in environmental geophysics because it's complicated and it's difficult to get good reflections for the upper 10 or 20 meters. Seismic refraction is more common. This is occurring when you have a layer at depth that has a higher velocity. And when you do this, you can get some nice results. Here is the Randa rock slide in Switzerland. So there was a rock slide here close to Zermatt, created some flooding, and the village was closed for some years. Here's the study site. This is colleagues at ETH who worked here. And why I want to show this result here is just to come back to this thing about 2D versus 3D. They did 2D seismic refraction measurements in this location, orientation, and this orientation. And if you now go to this location here, one model in one direction says that the velocity is varying like this with depth. Another orientation, say it's like this. Okay, then you could say, oh, it's anisotropy. But it's probably only because you have made this assumption, 2.5D assumption, that everything is the same in one spatial direction. So if you now work in 3D, you basically will come up with models that are consistent. So be very careful in working in 1D or 2D when the Earth is very strongly 3D. So seismics, very useful in many ways, and I think I said this basically, but for unconsolidated rock, you're mainly sensitive to porosity and profluids, and then if you're in more crystalline systems, it's mainly the mineralogy that will dominate the response. So briefly here, I will talk about the G-radar method, and then I will skip the gravity and the magnetics. So GPR is a bit of a hybrid in some ways between seismics and EM methods. Of course, it's the EM governing equation, same equation as before. It's just that displacement currents now is more important than the diffusive currents. You work in very high frequencies. So here is acting as a wave. So there's some analogy here to seismics. You send a short EM pulse from a transmitter. It moves through the surface, and then it's picked up. The energy is picked up by a receiver. You repeat this for different orientations of the emitter and the receiver. The velocity is given by the velocity of the light divided by the square root of the relative permittivity or the dielectric constant. And here is what is very nice with GPR, is that you're basically now, your velocity is related directly here to this dielectric constant. And the dielectric constant for soils is extremely well determined by the water content. So if you now work in an agricultural setting, you want to say something about the water content, you use the top equation. I think it's the most cited paper in water resources research. It's a very predictive relation. It's not perfect, and there are more advanced models, but basically this is one of the main attractions here with GPR. So here is a little modeling exercise by Code of James Irving. So here you essentially have seen the energy that's moved down. When you touch these different interfaces, the energy comes back. You measure this at the surface, and with different locations of your sources and receivers, you're going to obtain a section like this. You're going to migrate it, and then hopefully you're going to be able to say something about this subsurface that was responsible for your measurements. You can work with different antennas and different frequencies. So 100 megahertz, let's say that would be the lowest you would work with, 50, 100 megahertz typically, rather big. Higher frequency, smaller. So smaller antennas mean higher frequency, higher resolution, but it also means that you're not going to be able to see very deep into the subsurface. So here is the same section, 50 megahertz antenna, you see some details. You go to 100 megahertz, you see more, and you go to 200 megahertz and you see more. But you saw here you can basically see something, in this case to 8 meters. At the 50 megahertz, you had information down to 20 meters. So there's a trade-off here. And then you can get very beautiful images of stratigraphy. This is some sand dune somewhere in Africa, I believe. And sedimentologists can interpret this in great details. So it's very useful. And people that like seismics, they will also like GPR, basically. And here, what you also do is that you do cross-hole. So you would make your measurements in a borehole. You would receive the energy here in another borehole. And what you maybe saw here is that the energy, the information that you obtain here is not at all as rich as the information that you obtain from reflection. You're not going to be able to have the same resolution when you work in transmission mode as when you work in reflection mode.
Niklas,
yes?
For cross-hole, do you lower the antenna in one of the holes? Or
Yeah, so basically with the modern systems, you would have 1 meter. So you would have essentially decrease 1 in steps of 25 centimeters or something like this. And then the other one, you would be an automatic trigger. So you would move up with a measuring wheel, and you would essentially fire every 2 centimeters or 10 centimeters or whatever. So it's quite quick. So if you have, 10-meter depth that you're interested in, and you want to have a survey where you have information about every 25 centimeters or so few thousands of measurements, that will take you 1 or 2 hours. So it's pretty quick. Yeah. So when you do this, normally you pick the first arrival time. So this is the first energy. You will use this to try to recover the subsurface. The result will be nice, but not perfect. And what you can then do is that you can translate this into porosities, for example, because we said we have this link to water content. So if you're in a saturated zone, you have porosities. So you can talk about layers in a gravel aquifer. You can do many sort of basic things that are not very fancy, but useful. Then you can do full waveform inversion. So you try to explain all the data that you're observing, not just this first arriving energy. So here's some data, and you try to essentially, this is the measured data, and the image that was obtained by Anja Klotze essentially produces this type of data. So you're not just fitting the first arriving energy here, but all of the things.